Hello, wanted to spend some time going over the problem that we didn't get time to go over in class yesterday. This one was what we put up at the end after we started talking about ketals and acetals. So I just wanted to go over how you might use ketals and acetals in synthesis in a problem like this, because this is something that we're going to do relatively frequently. So what we're looking to do here, and I think the thing to think about when you're thinking about why we would use acetals and ketals is to think about how do you do a reaction where you have something that reacts with a carbonyl, in this problem like a Grignard reagent, and you don't want one of your carbonyls to react. As long as the carbonyls are different, or carbonyl type derivatives are different, you can do a carbonyl protection reaction like we do here. Right? So the idea here is that we have a ketone and a nitrile. Can we prevent the ketone from reacting with the Grignard reagent and then react the nitrile and then liberate the carbonyl again so that we can have the ketone to do more chemistry with? And so that's what we're going to see here. So in this problem, again, we have a ketone and a nitrile. We react it with a diol, catalytic HCl, remove water. This is our ketal forming step, right? And we can walk through the mechanism of this just for some practice, right? And one thing that I know some folks have been asking is, well, what does this cat HCl mean? So again, catalytic anything is that you're going to use that in the mechanism, but it's not going to be consumed in the mechanism, which means you're going to use it and regenerate it, use it, regenerate it. And so that's how we're going to use acid in this problem. We're going to use HCl to generate a protonated species, and then in the last step, we're going to regenerate HCl so it can continue to react in the reaction. Right? So as we said in class, if you have acid and you have a carbonyl, the first thing you're going to do is protonate the carbonyl. So that's where we're going to use the catalytic HCl, right? And we'll generate chloride. So now we've activated the carbonyl towards attack by the alcohol. Again, alcohol is a weak nucleophile. You have to protonate the carbonyl first so that you can then do the reaction, right? So now we're going to have the diol attack the carbonyl. All right, so we get to that point where we've formed a new carbon-oxygen bond. All right, we can now do a proton transfer reaction. I'll usually just write that as PT. We can transfer the proton from the alcohol that reacted to what was the carbonyl oxygen. Sorry, you've got the CN over here. Right, and this is where we do the elimination step in the mechanism. We've already done the addition step. Now we eliminate water. So water leaves, and then we reform a new carbonyl, right, which is going to continue in the reaction. And again, as we're going to use Le Chatelier's principle to drive this reaction, we're going to remove water. Right? That's why we have remove water in here. That'll keep driving these steps towards the product. Right? And now we can do an intramolecular reaction, right, where we're going to form our ketal. And when we have the alcohols in the form of a diol, we're going to form a cyclic ketal. And then the final step, we just have to regenerate acid, and we have Cl- around that we can use to regenerate. All right, so that regenerates HCl. And we've formed the ketal. All right, so all of that mechanism was just to get us to the Ketal. All right, so this is the Ketal. And again, sometimes you'll see folks will call this an acetal. In general, I always think about ketals coming from ketals and acetals coming from aldehydes, but often people will just refer to them as acetals. It doesn't really matter to me how you refer to them, but that's how I'll talk about them. So anyway, that ketal is the product of the first step, and you'll see we no longer have a carbonyl here. All right, and this is a ketal, not reactive with Grignard or lithium aluminum hydride or any of those other strong nucleophilic reagents because there's no carbonyl. This will be inert. We've got a cyanide. We talked about last time how that's going to be reactive with Grignard reagents. So now if we look at what happens in the next step, again, the carbonyl is no longer there. That's not reactive. Now we're thinking about forming a bond between the nucleophilic carbon of the Grignard and the electrophilic carbon of the nitrile. So we're going to add to form that bond, right? And like in the carbonyl, we're going to push electrons in the pi bond onto nitrogen. So what we end up forming is the ketal doesn't do anything. We've now added a methyl group, and we have N minus, right? And one idea would be that you would add another equivalent of Grignard to that pi bond, which is a really interesting idea. The problem being, if you do that, you end up with N2 minus, and it's just too unstable to form N2 minus. So you're only going to add one equivalent of a Grignard to this to get N minus, right? So we end up here, right? There's nothing else that the Grignard can do, so even with an excess, nothing else is going to happen. And now we're going to add acid and water in our last step, all right? So this is essentially the quench of the Grignard, and we're going to react with the ketal to deprotect that carbonyl. All right, so the first thing we're going to do is quench the result of the Grignard reaction. All right, so that gives us a functional group known as an imine. An imine is the nitrogen equivalent of a carbonyl, right? So carbon-nitrogen double bond is an imine, right? And since we have acid and water, we're going to continue our reaction now, this time with the ketal. We're going to run the reaction we just did up here, but we're going to run it in reverse, right? So we're going to do exactly the same steps, but in reverse, remembering that this is just an equilibrium process. If we remove water, we go towards the ketal. We add water, we go back towards the ketone. All right? So we can protonate. We're going to break open the ketal. Water can now add. We can do our proton transfer reaction. Now we can remove the diol, forming our carbonyl. So we'll lose the diol, and then we have the rest of the molecule. And then we can do another proton transfer reaction. This time we have water, so we can regenerate H3O+. All right, so that gives us H3O+. So that would regenerate the carbonyl, again, showing how we start with a carbonyl, protect it, do a Grignard reaction, deprotect it, we get the ketone back. Now we can do more chemistry of the ketone. One interesting thing about this reaction is that based on what we know, this is what we would predict as the product. And that's perfect, excellent idea for the product. The reality is that that's actually not right. And that we're going to see this in class on Wednesday, is that in the presence of acid and water, an imine is not stable. Right? It turns out that just like what happened here with the Ketal, the imine is going to react with acid and water. That's going to turn out to generate a ketone as well. You'll note we're at the ketone oxidation state here, and we're going to see a theme emerge that whenever we have acid and water, we're going to turn anything that is of the ketone or carboxylic acid oxidation state into those two functional groups. Right? So the final product and the correct answer for this would be a diketone. Right? And so what I would love for you to do is to try to work out this mechanism to figure out what happens to the imine, and we'll definitely talk more about that in class. So anyway, I hope this is helpful as you think about these new reactions. And again, our focus now is on thinking about weak nucleophiles reacting with carbonyls and to see how those are going to help us in synthesis.